Okay, welcome to Lab 11, and we'll take a look at the San Andreas Fault this week. And yeah, it's probably something that we can see as very close to home, something that's extremely practical to understand more about based on where we live, where our college is anyway. And yeah, I think sometimes in college, in university, in life, we learn things that might not uh, seem directly applicable to our everyday life. And so I guess there's a little bit of excitement in me today, just how immediately practical the understanding of these fault lines as part of the San Andreas system, how relevant they are to our life. As a geographer, I see everything that we've studied as very relevant to our life, but something with as big of impacts as this lends itself to excitement even more so. So, it's the boundary between the Pacific and North American plates, which I'm sure you've learned quite a bit about in a physical geography lecture. It's a transform or transcurrent fault, and specifically a right lateral strike-slip fault. Okay, and it extends from the Gulf of California all the way to Cape Mendocino, so over 800 miles. Here's a little map of it, right? Here we are down in the Gulf of California and in Mexico. And the fault continues all the way north through California and off into the Pacific Ocean there, underneath the Pacific Ocean that is, and then just heads northwest, just around Cape Mendocino, just a little ways north of us. And get a sense of some of the other significant fracture zones around the west coast of North America as well. This is a very significant subduction zone off the coast of Northern California up through Oregon, state of Washington, and especially here off the coast of Vancouver Island in British Columbia. And these very significant smaller plates that are there. So that's just a bit of the surrounding geology as well. Some of the other fault lines. It's pretty interesting that just north of us there's a subduction zone, also highly susceptible to very significant earthquakes. And underlying the Cascadian volcano system, which the southern extent of is Lassen volcano, just in NorCal as well, and just northeast of Sacramento, and then Shasta and Mount McLaughlin, and continuing north from there. So here we see a little satellite image of the San Andreas Fault cutting through Point Reyes, and that's pretty interesting to see how it can affect surface topography as well. This large bay on the northern part there, the Estero or Drake's estuary here. And then we can see that, on an aerial photograph, what that looks like. And then south from there, what the San Andreas Fault looks like down in the western part of the Central Valley. Another photo is from there. And here we have a picture of our Wallace Creek that we'll be working with this week. This is with the caption, "Stream offset along trace of right lateral San Andreas strike-slip fault." It's pretty interesting to see how the creek, which would have been right here coming out of this Wallace Creek drainage, has now strike-slipped, right, because of the Pacific Plate, which is on the foreground, if you will, of this photo. We get the, we're viewing west here. It's on the western side of the fault. The Pacific plate here is moving north in comparison to the Atlantic plate. In the foreground. Sorry if I misspoke before. In the background is the Pacific plate. Foreground is the Atlantic plate. So as they have shifted, this drainage now is not where it would have been coming out. Yeah, so pretty neat how we can see that from aerial photographs. A little more about it here. While it may appear as a single fracture at some location, it's actually part of a complex system of subparallel faults. Okay, that also includes the Hayward Fault, very importantly, we'll take a look at. San Gregorio. It's always interesting to try to bridge our Spanish and English pronunciations. San Francisco, right? Yeah, so and to be honest, I don't know how to correctly pronounce Gregorio in Espanol. Yeah, we don't see a lot of Gregs in Spanish, at least in my Latinx friends. And the Calaveras, right, fault, the Concord, the Rogers Creek, Greenville. Okay, so here we see a lot of those mapped out. Very importantly, the Hayward Fault running through the East Bay. There's Rogers Creek just north of that. Just to the east of Hayward, the Calaveras Fault. Here's Concord Green Valley. There's the Mount Diablo Thrust Fault. Over to the east further yet is Greenville Fault. So a few slides back I misspoke and said the Atlantic Fault, the Atlantic plate. What I meant to say is the North American plate. For some reason I thought that was coming off there. It sounded weird when I said that. And you see the directionality there, the North American plate moving southward compared to the Pacific plate moving northward. And we know this most vividly through tracking, GPS monitors, one being mapped out here on the Farallon Islands GPS site, and then one up in the town of Columbia, or village, which if you haven't got a chance to explore, it's a really fascinating area, in particular for geography or in geology as well. But yeah, also a really neat junior college there, community college, that I went to. So yeah, so that's really neat to see these different fault lines, because usually we just hear of the San Andreas, perhaps a little bit more so the Hayward, based on where we are, or where our college is, and being East Bay folk. But yeah, some of these other ones, like the San Gregorio there, going right along the coastline, pretty interesting. And here's a little map of the seismicity of Central California, 1980 through 1986. So this is only 6 years. And you see all these little dots representing different seismic events, different, a whole range and different size of earthquakes along, well, the San Andreas and Calaveras faults. So I guess, perhaps more than just 86 to 80, and considering it has the 89 Loma Prieta earthquake on there, but maybe they're just adding that for reference, to the location of where that occurred. Yeah, really interesting spatial distribution of that. You can, begin to see the Hayward Fault quite clearly here as well. So here we have this. Yeah, one of the reasons why I emphasize why it's so practical to understand what's where we live, and this fault system in its relevance to us, is the extreme ignorance of the location of these oil infrastructure and what we call in geography geoignorami. You can see here the Valero Venencia refinery, the railroad bridge, the Tesoro Golden Eagle refinery, quite close to us, and then as well the Kinder Morgan Concord pumping station, all located very close to the Concord Fault. So highly susceptible to damage and destruction and potential disaster from earthquake along the Concord Fault, and you know, the Hayward Fault being quite close as well. Even the San Andreas and some of the other ones we saw, a slip event on those, depending on its severity, could likely produce, you know, enormous consequences. When you factor in the potential for fire as a result of this, and the huge amount of just precariousness that presents, this is a very serious issue for our region. Something we should keep aware of and change, really. So here we have the Hayward Fault mapped out through the East Bay here. It's a subsidiary fault to the San Andreas. It's considered dangerous because it runs through the heavily populated cities of the East Bay, transects vital transportation and utility corridors. Right, so lots of our water main lines coming from the Sierra cross this fault, and that's very serious. And freeways and highways as well, and then significant gas lines as well besides the water lines. So again, really important to keep in mind, and hopefully some of you will go on to be planners and engineers and geographers and can work towards creating more safety and sensibility around these issues. So out of the Bay Area's population of about 7 million, 2 million live in close proximity to the Hayward Fault alone. This is pretty interesting to see 1906 compared to currently, or at least 2015, and the urban areas of the Bay Area then, a little bit in San Francisco and a little bit in the South Bay, but you know, East Bay there having pretty similar size to San Francisco, and of course that's greatly magnified 115 years later. The amount of urban area, urban development, but I mean it's crossover with the spatial distribution along the Hayward Fault here is just staggering. And yeah, so it's more to keep in mind. And so we, you know, to look a little bit at landforms produced by strike slip faults, we have this horizontal offset, the offset stream we saw a little bit further up there, and we'll come back to that. But linear troughs and valleys are a potential, small depressions, and this can include vertical offset as well. So here you see how a highway has been offset, and then the fault lining running right through a farm field. Here's a picture of, you know, these bricks would have been laid down right in line with each other. This is the fault creep along the Hayward Fault, has offset this Oakland street curb along with a fiduciary mark made with a concrete saw. It's by Andrew Alban photo. So when the curb was laid down, this saw was this little, they put this little mark in there, probably by a geologist to, or whoever Andrew Alden is, geographer, earth scientist, someone interested in tracking this, knowing right where the fault line runs, the Hayward Fault. And so, you know, we don't know the span of years here, but there's various places you can go along the Hayward Fault and see, even in the course of our lifetimes, how it has shifted. So here's another example of that little aerial shot of looks like a sound barrier wall, and the fault running right through this, and the utility district having to reinforce the wall with a steel structure here based on it splitting. So to move into a little bit of the exercise then for this lab, we want to start calculating the average rate of movements along the fault. This is also known as the slip rate. This is the measured distance along a portion of a fault over a number of years that the displacement has occurred. So generally expressed in terms of centimeters per year. Okay, and so also known as the slip rate, like we said. Yeah, I'm not missing a slide there. For example, if you measured 32 centimeters of displacement over a 15-year period, this would be 32 divided by 15. And then to come up with centimeters per year, we've just continued the equation outwards there, and then coming up with about 2.13 centimeters per year. So, or if an average slip rate is assumed and the offset is known, the number of years required for the offset can be calculated. For example, what is the number of years required if an average annual slip rate is 2.2 centimeters along the measured displacement of 23 kilometers? So we're kind of just playing math equations here, but in a spatialized sense, but calculating different variables in the equation. So if we know our displacement rate of 23 kilometers or 2.2 centimeters per year, we know that, not the displacement rate, but the displacement has been 23 kilometers and the slip rate is 2.2 centimeters per year. Well, then we can multiply that out to come up with 2,300,000 centimeters, and that's a pretty large amount of centimeters, right? So in general, or not in general, but where this leads us is that 1,045,454 years it would take us to go that 23 kilometers. It's a pretty long time, but not a insignificant slip rate to think about. Almost an inch, right? An inch is 2.5 centimeters, almost an inch movement along that fault per year. So to get back, get back to our Wallace Creek example. Here's a aerial photo of that again, a different one, but can see the offset here, and this picture is in the lab for the week as well. You have a scale here of 100 yards. It's about that distance, and yeah, the San Andreas Fault running right at the base of the hills there. It's where the drainage, the Wallace Creek drainage, would have came out, and now it's just draining down along that fault and continuing out. There was some weakness there that led to it to jump its stream, but its course, or carve a new one. But you can see further down, further south, that is its ancestral drainage, as they're labeling it, and here we have the topographic map of that same viewshed, if you will. So you have the younger channel and the older channel, alluvium, and the fan and slope wash in yellow. And yeah, so that's a little bit of a contoured interval of 10 feet, it notes, and our scale bar there. What my picture, might just be hiding is some of the different time scales associated with the different color bands. And yeah, so we'll work with those in the lab, and let me know if any questions come up for you related to the questions there. And yeah, I look forward to hearing from you. Thanks, take care.